Good morning, everyone. Good morning, world. Nice to see all of us here today online in this special time. My name is Junling Shi from National Central University, Taiwan. It is my honor to introduce a very nice and wise lady, our first keynote speaker, Dr. Sherry C., the principal scientist of BCSC Science Learning. For over 20 years, Dr. C has brought her R&D leadership to the creative design and wide array of STEM learning applications. She has worked at Exploratorium in San Francisco, directing new media research and evaluation to study informal learning. When she was at UC Berkeley, she co-created the Tech Hive Studio, the howtosmile.org digital library, and health apps for Children's Hospital. She worked closely with Anne and Mark Eisenberg from the Craft Tech Lab at CU Boulder on paper mechatronics, and most recently with the Concord Consortium's InSpec project, researching the integration of IoT-enabled sensors and computational thinking with science practices to support student-centered data production in science classroom. Her design-based research has been published in books and journals, and has served on the editorial board for the informal learning strain of the Journal of Learning Sciences. In today's talk, she will talk about design for learning that places value on learners' agency, materiality, and social participation. She will share with us her recent project in CS for All, computational thinking in high school science, use computational craft making, and teacher professional learning. Having that said, I personally cannot wait to know more about the details of Dr. C's work. Without further ado, let's welcome Dr. C to give her talk on designing for more learner agency using computational tools in STEM. Dr. C.
Thank you very much for that lovely introduction, Professor Shi. I'm so happy to be here, and thank you for the invitation to speak at the CTE-STEM conference. I'm really looking forward to sharing my perspectives on how to design for more learner agency using computational tools in STEM. If you give me a moment, I will share my slides. Okay, so before I begin, I would like to share my deep appreciation and acknowledgement to the wonderful collaborators I've had the chance to and fortune to work with. I also want to acknowledge the support I've received from the National Science Foundation as well as the Gordon and Betty Moore Foundation for supporting my research. So a central theme of my talk and my work is learner agency and how to foster this through design. I view learner agency as the capacity of learners to make their own choices, to take action to advance understanding, and to take responsibility over their own immediate and future learning. So learner agency using computational tools in STEM is important for enabling students and teachers to act and fully participate in a computational world. So the theme of this conference is computational thinking in STEM education. So why this topic? The other night after sunset, I went outside of my house and I looked up at the sky and I observed a pattern of bright lights. I wondered, are these naturally forming or man-made? These low orbiting satellites keep us connected to our wireless devices and information. I actually don't know how exactly they work or what they are doing. Maybe they use AI or machine learning or data science. Perhaps they are used to collect our data for an unknown purpose. This raised even more questions for me about the future of computing. How do we find out more about these black boxed engineered computing systems? And who gets to decide what goes in the box and how many of these go into our airspace? I think we need computational thinking in STEM so we can be empowered to understand and feel in control of the computing taking place all around us. So back home, in this unprecedented year of COVID-19, one might call this the year of screens, We have relied on screens to go to work, to send my son to online school, to mentor students, to care for our elders through telemedicine, do exercise classes, and even go to online birthday parties. Yet my relationship to computers brings up very mixed feelings about the role of computing in education and how this is impacting the lives of the less fortunate. The pandemic has forced us to participate in a computationally driven world, but has also created an even greater divide in education between those who have access to screens and those who don't. So how do we respond to this inequitable situation? And what do we know about computational thinking and how people learn with computers that might help us in this ongoing educational crisis? So the idea of computational thinking in education is not new. We've had at least 40 years of research and practice to design computational experiences using what Seymour Papert called objects to think with together. Computational objects are the building blocks to learning things like 3D geometry or practices like troubleshooting and modeling. And since the writing of the seminal book Mindstorms, computational thinking has continued to grow. So in the middle of this timeline, in the early 2000s, there was a recognition that computational thinking wasn't just for computer science professionals, nor bounded in the discipline of computer science. Computational thinking, or CT, is a necessary part of critical thinking, problem solving, and learning. In middle school science, computers were designed as learning partners for supporting integrated understanding of science concepts like the difference between heat and temperature. And CT as a practice is used for constructing computational models or teaching students the practices of science. So during this middle period, the field of cognitive learning science has expanded to recognize and acknowledge that situated learning and social participation mattered. So more recently, and here we are in 2021, the critical framings of computational thinking challenge prior views of CT to place equity at the center of computational participation. So how should we address these ongoing inequities that continue to persist between different genders, classes, and races? So as many of you may know by reading many different reports and articles, that we haven't yet reached a consensus of what computational thinking is. And I don't think we need to reach a consensus to define nor define a universal construct. So I feel that we can let 10,000 flowers bloom. We need just enough common ground or shared soil, if you will, to make progress in K-12 education. So my definition of computational thinking and how I view it are acts of agency and empowerment through solving problems and designing systems in the context of computing. And computational thinking is participation with others to collaborate and make use of computational materials to advance their own purposes and purposes of their community. So this is a definition I'm going to be working with as I share my work. So I will share 3 stories of CT in education that involve using hands, not just screens. Paper Mech. This takes place in out-of-school learning environments using paper crafts enhanced with computational materials. The second story is Inspect. This takes place in school in high school science class using Internet of Things or IoT sensors to produce data. And my final story is a recent project called Unblackboxing Computing. And it's a physical computing project for beginners and underrepresented youth. With each story, I focus on 3 design considerations. These are lenses to help promote learner agency. social participation, materiality, and equity. So as a quick reminder, this is my definition of learner agency. And to support learner agency, I use these considerations, social participation being the first one. So this is the idea that learning from each other through collaboration and social interaction and shared activity to support individual and group learning. The second design consideration is this idea of materiality. So using tangible materials as a medium for exploration, investigation, composition, and critique. And art teachers should be quite familiar with this idea. And my third consideration is equity. And this is a vision that all learners can fluidly participate with access to human, material, and technology resources needed to be successful. So really no barriers here. And it's also a perspective that views learners as belonging and capable of computational thinking and technological innovation. So with those three design considerations, I'll start with my story of PaperMech. So with my collaborators, Ann and Mike Eisenberg at the University of Colorado Boulder, and Hyunju Oh, who was a graduate student at the time, who's now at Georgia Tech, we together developed a craft-based approach to teaching creative engineering using computationally based materials. So our vision for PaperMech was that it's a multidisciplinary approach to learning engineering. And it's a view that everyone is a maker. So social participation happens via a diversity of different activity structures. And by using paper as a medium and enhancing it with computation, that we can invite a broader participation in STEM. So there are a number of resources that we created, both physical and online resources. I encourage you to check out the website. And we use to support different phases of the engineering design cycle, where we ask students to imagine, design, build, test, and refine. One of the resources we developed was called Fold Mecha. This is a motion simulator that a learner selects from a basic set of movements. There's two different screens that one can access movements using traditional engineering vocabularies like a rack and pinion or spur gears, or they can use everyday words like up and down or round and round, and to use those motions to imagine and build a machine. So students use this to both do imagination and design planning. Fold Mecha also is used to generate files that are ready for laser cutting using different design parameters by adjusting the sizes of gears, and it provides an output that can then be sent to a laser cutter for cutting pieces. Here are some of the parts that were cut from cardboard. So when we ran workshops, we usually set up a buffet full of materials and give students lots of choices to pick out the materials they want to use. As a design consideration, it was important to support learner agency by giving teachers many choices in what and how to teach. For instance, we've developed a number of different microcontrollers. Some were appropriate and some were off-the-shelf commercial products that were appropriate for younger children. And we also had Arduino versions, ones you could breadboard, and even super cheap ones called a DIY cardboard that students could program an ATtiny and solder their own little card for less than $1. So here, just to give you an idea, is that in the process of going through this engineering design process, there are many different ways of organizing activity and different activity structures. And this is why I have this purple line and these stars, to illustrate that there are many processes. And I'm going to walk you through one example of a process that we had taken students through. So we have students find a story, and this is where they do some ideation and try to plan what they want to make. We have students and teachers alike do envisioning, with sketching on paper and trying to imagine what they like. And sometimes they can also do that in the, they can do that in FoldMecha as well. Oops, excuse me. Here, they can do some design work. They also spend some time specifying what their design would be. And so we blend both the mechanisms of the pictures with movements of what they planned. And so when they see a movement that goes like this, they may say, oh, I think I want to develop an owl or maybe a flying penguin. So after they've gone through this ideation phase and thinking, then they go to start building their machine. And this is where tinkering with different mechanisms, interacting with the electronics, and trying to make the machine come alive. And this is where they design, they write scripts and coding to make it match to what their vision is. And they also have are interested in kind of decorating and trying to make their animal look what it looks like. And finally, at the end of this phase, we always have a celebration phase where it's a public display and sharing of what are the highlights, what are the things you learned, and what are the things that you feel like you can improve or want to learn more or get better at. So that gives you just a sample of an arc. So here are some ways that we framed the design activities and social participation. For instance, one can organize the activity as designing a mascot for a team in need of a cheer. And so that has a personal goal of your mascot, but also cheering up a whole team. Perhaps you want to create something for a younger sibling or a family member. You can also choose to, if you're tying this to literacy, to pick a favorite storybook character and animate that using paper mech. You can develop an instrument that then becomes part of a larger band, or designing an animal for a robot petting zoo. So we tested and implemented paper mech in very different settings, mostly out of school settings through facilitated workshops. So this happened in children's museums, in maker spaces. We did this on Zoom as well in community workshops. And learning is through social participation through collaboration and the social interactions in a shared activity. So we're supporting both individual and group learning. So we had a number of research goals and design intentions, which you can read about in our paper. However, the big outcome for me is that our vision was realized. We used computationally enhanced paper crafts to invite broader participation in STEM. And these are just a small range of the projects that youth had developed, and they generated a diversity of ideas. And computational thinking wasn't just coding on a screen, but it was coding for a purpose. So the purpose was to tell a story, or to make a ballerina dance, or make an animal wiggle, or make a crab walk. So coding was for a particular personal purpose as well as a social purpose as well. And of course, we were very happy to see that the teachers also had a diversity of ideas and in coming from these just a set of basic movements. So in terms of observations and findings, we observed that framing can invite multiple starting points and diverse pathways. And we also observed that there were no two designs are the same, that everyone can be a maker. With respect to materiality, the familiarity with paper, which can be found in school classrooms, open up space for creativity and expressivity. The paper could be drawn on, and painted on, and decorated. And because cardboard is also just very forgiving and very cheap, that you can throw out your prototypes. And so the affordance of paper and cardboard as a medium also enabled engineering practices of prototyping, testing, and design iteration. So I'd like to now move on to my next story, which takes us back into the science classroom called Inspect. So our envision for Inspect, which is an acronym for Integrating Science Practices Enhanced by Computational Thinking project, was to improve science learning by including laboratory experiences. We wanted to necessarily integrate computational tools and science practices together to address the next generation science standards. And we also wanted to take this idea of this Internet of Things sensors and actuators that could be used for a kit in science classrooms. This project, funded by the National Science Foundation, was a multi-year design-based research project with multiple conjectures. We worked in both urban and suburban high schools and with a number of teachers. And using a storylines approach, we created a 3-week-long unit on photosynthesis and cellular respiration using sensor data. And along the way, we also developed software in a kit called DataFlow, which students could then tinker with their data and their setups. So our anchoring science phenomena focused on CO2 in our atmosphere. So when plants respire, and they consume CO2 gas at different rates depending on the amount of sunlight. And plants remove carbon dioxide gas from the atmosphere. So when you look at a tree, you can imagine this tree was made by the gas that's around it that got converted into matter. So with the Concord Consortium and many labs together, we created a kit of Internet of Things sensors and DataFlow software to program the sensors and actuators, which students used in their experiments. We went through multiple iterations, but this is a snapshot of the latest version. And so using DataFlow, students could drag different blocks onto a workspace and then connect the blocks using wires. And that was the metaphor of data flowing through a system. So students could select one of many sensor types. They could also select how long they wanted their experiment to be. And because this is biology class and it takes a long time for plants to grow, you could have an experiment that is running for as long as 30 days or as short as 5 minutes. So students had that choice. Students also had to be very intentional about thinking about how much data would they need in order to support their theory of what was going on with their data. And so they also had those parameters within the DataFlow system. And so this system was used to then program the sensors and then start the experiments. So our initial framing for a lab experiment was most like lab experiments using sensors that tended to replicate something that had already been discovered by a scientist or was done in a science classroom the year before, and the year before that, and the year before that. And so here's a standard prompt for a lab. Use a gas sensor to measure carbon dioxide gas consumed or produced by a plant during respiration and photosynthesis. So what's common in this laboratory is that students would follow a very careful set of procedures to get a measurement. So for example, they would get a container, like a plastic a food container, and very carefully take out 20 leaves of spinach, one that you can get at the grocery store, and then carefully place the 20 leaves inside the container, plug in their sensors, and then put the lid on. And the lid could be plastic wrap with a rubber band, and then measure this, and then report what that result would be. So this is a very kind of standard procedural laboratory where precision mattered to get the result one would expect. So what students would find when they did this laboratory is that in the light, which is the graph on the left, the plants would begin to photosynthesize, taking up CO2, and the overall CO2 levels would drop, going down this way. And in dark conditions, so if you take that container and you put a towel over it or a piece of aluminum foil, you find that plants do cellular respiration, and overall the CO2 levels rise. And so this is the standard result that one would get. So with respect to agency, I want to argue that this type of lab and design was problematic. It was problematic for promoting learner agency because the results were predictable. These are predictable outcomes. There's limited authenticity in this lab. The students kind of know what they're going to get, and they're kind of following and going through the procedures. And these sorts of labs set students up for failure if you're the kid who doesn't get the exact same result as the person next to you. And it's also fosters low interest. In this particular lab, while there were some hands-on things, it also limited materiality in one sense. It didn't really take advantage of the full affordances of an Internet of Things computational system. So it turns out with the data flow system, one could set up an actuator, like a lamp. And you can set up logic in the data flow system to say, when the CO2 reaches a threshold, turn the light off or turn the light back on. And so you could program the data flow with different logic. And so by using this computational system, you're interacting with the biological phenomena and coming to understand it in that way through computation. So this is our revision. So we revised the framing instead to ask students, what does light have to do with plants and CO2? So this became the driving question that then opened up space for design. So we asked students to explore plants in light and dark conditions. We didn't tell them what they were going to find. We said, just go explore in light and dark conditions, and you decide what light is and you decide what dark is, right? And we found that students could be more agentive. So we were very fortunate to work with a teacher, and this particular teacher was a maker teacher who valued equity, materiality, and social participation as he set up a classroom with many choices. I'm going to share just a couple examples of what we saw in the classroom. So Jose was a student who wasn't particularly interested in science, but he was very motivated in the science lab to make better data. So Jose designed an experiment using his own ideas. He wanted to improve the CO2 signal by drawing out air from the container before each trial. So he built a bag and he put it around the container, and he tied a straw because he was convinced that the amount of gas inside of it as a starting condition would make a difference in the graph that he would get. And so he set up the straw and was very intentional and careful to suck the air out of this this container, right? And one would argue that's a scientific practice, is doing these iterations and being careful and trying to understand and make sure your technology is working in the way that you would expect, and reflecting on that data and the results that you get. And during this experiment, he noticed there was a tear in the plastic. So he started speculating maybe the graph was because of a leakage through that. So he went back and tried to change his setup to be a little stronger, to make sure that his system was set up properly, and he wanted to get and really work towards getting a better sense of the data for his experiment. And so we see this as a win because he both used a number of different materials to support his discovery process, but also interacted deeply with the phenomena as well as the computational tools to learn science. So my next example are a pair of students. And because we had one set of Internet of Things sensors and materials for the class, I think we had like a set of maybe 15, And so in a class of 30, you could pair students up, or in a very large class, you can have groups. And we did like setting students up in groups so they could have conversations and argue with each other about the results. So in this case, we had a pair of students, Linda and Winnie. And Linda and Winnie worked together, and they noticed that Fernando's data, as they peeked over, they saw his data and they were very suspicious. So they critiqued his work, and they hypothesized that his data was due to heat and not light. But they wanted to be able to test their hypothesis. So using the materials in the classroom, with a very motivated teacher who provided these materials, they tested the data under extreme conditions, under two conditions. So they decided to put their container in an ice bath to look at what would happen with data in freezing cold conditions, and then also in boiling hot conditions using a hot plate by putting this on. And in their view, they really valued getting to do an original science experiment, something that no one else is doing. And this is a practice of science, right? Trying to advance the field by doing original science and also critiquing your peers' data and doing an original experiment. And so they also use tangible materials as a medium for exploration, investigation, and critique. So there are many stories like this in the Inspect project, where students were able to collect and produce their own data. And students had designed novel experiments. So with respect to learner agency, we see that students were agentive because they had a chance to be in a position of building their capabilities and bringing their ideas and building upon their own assets into the science class. So with respect to our observations and findings, I have included two references to papers here that I encourage you to read, and some references at the end of my talk as well. But I'll just share a couple of the observations and findings here. That the materials, including the software, the computational system, plus the laboratory materials, enabled students to be data producers. They were not consumers, they were producing their own data from these experiments. And when we shifted the framing to be less procedural and more agentive, we observed high agency among the students, especially those who the teacher reported to us were not interested in science. So the hands-on STEM labs with computational thinking could be viewed as a gateway to those not inherently interested in the topic, and we see that as a win. So the final story I'm going to tell today is a project funded by the National Science Foundation, CS for All, called Unblackboxing Computing. So back to my original story when I was talking about low orbiting satellites and not really understanding what's inside those boxes, this project is hopefully addressing some of that. So most computers do very powerful things, but they hide their inner workings. Even when students can look inside of a computing device, maybe take apart their cell phone or open up the inside of a computer, they would find it difficult to understand and difficult to manipulate its behavior. So in this project, we are developing a set of tangible computing materials that are teaching concepts to beginners through what we're calling an unblackboxing approach. So this is making the black boxes of computing visible, accessible, and transparent, especially for those who are historically underrepresented in computer science. And this particular project is challenging this idea that there is lots of coding that's going on, and coding opportunities, hour of code, but yet we still see a huge discrepancy between who gets computer science and who doesn't. and who views themselves as a computer scientist or coder or programmer and who doesn't. So we are in this project doing a couple things. One, we're building on the advances of material science, of human-computer interaction, and low-cost electronics to develop computational crafts. Very similar to our paper mech project, but instead of working in engineering, we're working in the discipline of computer science. So the computational crafts are blending computer science, art, and engineering to make the functionality of computers more transparent. And like the paper mech project, we really want to foster and enable expressive computing experiences. So we believe that these experiences can broaden participation in learning about electronics and programming and basic computing concepts, and that hopefully we can create new communities with the values and purposes that are markedly different from those historically tied to computing, robotics, and electronics, while also engaging youth in technical skill development, computational thinking, and programming. So the tangible and connected learning media supports learners in understanding computational concepts and practices, and hopefully we can build their competency beliefs, change their perceptions about who can be a computer scientist, and even maybe change their ideas about computer science, and helping youth and learners see that computing is relevant to their lives. So we also have a vision. This is a very early project, and so we have lots of ambitions to grow this in many directions. That hopefully that teachers and students, because teachers are also part of our audience, they can flexibly construct these technologies to be shaped and repurposed for their own ideas. And so when we see this appropriation happens, we feel like learners are at the center of the design, and that's when we start seeing agency. So computational artifacts and systems are constructed from the ground up. They're constructed by hand. They can be disassembled to be inspected and iterated upon. And the idea of this, computational systems could be unblack boxed, and we can demystify computer science. Okay, so two of our driving questions or research questions are, how does creating computational artifacts foster deeper understanding of computing systems? And our second question is, which aspects of the co-designed learning experience contribute to conditions for inclusive participation? We are necessarily engaging in a participatory design process, which we call co-design, where we're listening very carefully and working together with the users of the systems, teachers, youth, educators, software engineers, to listen to what are the processes that can help develop these materials that will be usable. So here is just a tiny peek. This is version 0.001. Very early work, where we've developed these sensor cards, and we will be developing actuator cards. And this is all paper and copper tape, and we're testing out different microcontrollers to bring materials to students. And we are teaching concepts of resistance and capacitance, and using different kinds of materials, because we're trying to make innovation on these printing technologies using silver, as well as doing different kinds of pressure-sensitive plastics. We're also looking very carefully at how one might use painting and drawing, especially with conductive paint, as a medium for exploring circuits. So this is just one example of several inputs, a pressure sensor. And so we developed this base card, which you can then take a sensor card and place on top, and these are all made by students. And then we also have different everyday applications, such as a step counter uses a pressure sensor. But each sensor card has a unique way to interact with it and sense inputs. And so we consider these as physical computing paper interfaces for projects. Here's another example of two different cards. We want to bring out the concept that there's a difference between analog inputs and digital inputs, and what's the relationship between those. And so in a digital sensor, which then you can translate to very simple computing concepts of 0 and 1, on or off, true or false, that you can use a context switch to teach digital sensing. And analog inputs could be used from measuring inputs that have a range of values. And so you can consider bending, like turning the volume of music, or continuous variable that would be taking this analog signal and then translating it. Okay. I think it's important to mention that there is programming involved in all of these projects that I've mentioned before, but the priority is around using hands and hands-on materials first to explore the possible applications and concepts before getting into the code of how it works. And so people have a purpose of why you want to use code, and not just start with the coding first, right? But it starts with a project and an idea. We have a number of design conjectures that are related to youth identities and competency beliefs, and how to create future computer science learning opportunities through a culturally responsive computing approach and through this co-design approach I mentioned. So we have a number of conjectures, and this is a TBD as this is a project that was just started. So I look forward to sharing more about this as we do more and work more with students this coming year. So those are my 3 stories. And now that we've had a chance to hear them and learn about some examples of ways to support learner agency, I hope they can be useful to you. The considerations of equity, social participation, and materiality, they've been useful for me as a researcher and designer to create learning that integrates computing and computational thinking with STEM in an integrated way. So to summarize, reframing can help promote learner agency. And computational thinking in education is more than just screens and coding. We want to position and prepare K-12 students and teachers to be producers and makers, not just consumers. We see everyone as a designer and a creator. And so I feel it's important to try to open up space for tangibility to support learning as well, and not just kind of typing in screens. And this idea of designing for equity, I think it should be mandatory. We've had 40 years of computational thinking, and it's important to really think about computational participation seriously. The computational thinking, which includes the skills, practices, cognitive processes needed to make sense of computational systems, I think for us students to participate fully, this is needed, right? So, this is a story yet untold, but based on our early work, is that we were feeling that this idea of co-designing with users is an approach that could promote learning for everyone. So researchers, teachers, and students all learn in the process as we're co-designing, rather than designing something and throwing it over the wall and expecting it to work. Oops, excuse me. So in conclusion, we have a shared responsibility to ensure that all students and teachers become capable of producing and creating with and in STEM and computing. So I've just shared 3 considerations, and there are probably more that you have based on your expert practice, based on your research. But I do hope that these lenses will be helpful to you during the conference and in your teaching. So with that, I want to thank the presenters, and I'm happy to answer some questions.
Thank you, Dr. Shi. Now it's the Q&A time, and I'd like to ask our little helpers to find some questions from the chat bot and ask.
Well, good. I'd be happy to answer any questions. We have our first question in the chat. And the question is, do you have project-based assessment or rubrics for the craft-based projects? And what are the suggested evaluation aspects? Yes, because this was not an in-school project, we did not have a formal assessment for these. But I would enjoy a collaboration where we align these to standards and do come up with those rubrics as well. We had the benefit of working in informal learning environments where there was lots of joy and work and extended time, but taking it into the classroom, I think, would be a next step. We did, however, give a lot of pre-post surveys to look at different aspects of kind of how they felt about their design and the work that they did, but I wouldn't call that an assessment per se, but it was more of an evaluation.
Okay, so we have a question too. What are the qualities of a good facilitator of this kind of learning, and how do we support teachers who are used to directing students exactly what to do or who to teach, or who teach in a high-stake testing systems to change their mindset and practices?
Yes, I think that's just a wonderful question, and that is the, I think, the very difficult part, because we did see teachers who were very didactic, and I think it really depends on what your goals are, right? So in our goals for Inspect, we did have the goal of making sure that students did learn the content, but more importantly, we wanted students to stay in science. So we didn't want them to just do well and then not care about science and not take any more science classes, but we wanted them to come to class engaged, and maybe internationally there might be less of an issue, but I think having students stay motivated to come to school and stay in school was also a motivation for us. So in terms of ways of facilitating learning, I feel like the different kinds of shifts that teachers would need to make to ask a prompt that would allow for a little bit of creativity or a little bit of kind of learner-centered agency could still result in high quality content learning. We did do a content assessment pre-post and did find that with very low p-values that students did do well on that. So I feel good about that you can still shift a prompt to open up for more design work and more creativity. And so in terms of a good facilitator of this time of learning, I would say that look at the assignments that you're giving and look at the kind of work that's being generated by students, and do you see some diversity in ideas and some interest by students to continue learning in that way. And there could be a small shift that you can do in your teaching to support that.
Thank you. We have another question. How long does the completion of a craft-based project take? For example, in Fort Mecca, what is the time and space requirement for the workshop?
Yes, that's a great question. We find that a minimum of 2 hours would be ideal. I think it's very frustrating for learners to try to do something in 1 hour. And we've, of course, had more success in doing something over a 3-hour period with a break in the middle. So this gives students a possibility of brainstorming and developing their ideas and gluing things together. The youngest groups we worked with were 9-year-olds, and they because their hands are much smaller and they also eat a lot of snack and they do a lot of socializing, it took a much longer time to get the project done, and they requested more time and they wanted like an extra morning to do it. So I think altogether it was 6 hours spread out over 2 days where they were able to build things. You can do things like shortcut processes. So our original plan was to have kids design things, and that we had a teacher in California who had children design things with Fold Mecha, and then she personally laser cut each of the designs that the students made, but it was very burdensome on the teacher. And so we shifted our model to say maybe we can just pre-cut all the materials like a library and a buffet table, and so students could make some choices or maybe some controlled choices to get to be able to make something. And also, I didn't mention this in my talk, but we really try to hold the kids back from decorating too much because they want to get to the decoration first, but we really want them to think about the mechanical engineering and the electronics and the programming.
So in terms of the space requirement of the workshop, how do you arrange your lab?
Yes. So usually there's a table of examples. So we like to have examples from previous workshops. So the kids like a gallery, like a museum, you put your hands behind and you lean in and you can see some examples. We also set up an area where we put all the craft materials, the decoration and the feathers and the eyeballs and the sequins. And then we have a table that is just the mechanical components. And because it's not common to have too many glue guns, for instance, with young hands, we set up a station that is a gluing station. So if they want to come to and bring their design and they can glue it, and so a teacher can help them glue there for safety reasons. And we also have set up things where for advanced students, they like to have their own microcontrollers, but for younger children, which they want to basically test and testing and refining, we set up a station of a microcontroller already set up. They can bring their designs that have a motor on it and simply plug it in and test it that way. And so they can take it to the testing station. So you can imagine there's lots of materials that are kind of surrounding the classroom while the group activity happens in the middle.
Wow, amazing. We have another question. Question goes, I'm wondering if you could delve more into the data production framework used in Inspect to find out how students perceive and make sense of the data that they are collecting. What sort of prompts or what sort of features in the kit software guided students to develop their own agency around collecting and interpreting data in a less structured manner?
Yes, I think that being able to let them explore the software first, and the way that initially when we organized the laboratories, we only had sensors because we had not developed the actuators yet, but found that students were more interested in the actuation part, right? So concepts like reaching thresholds or trying to keep a stable value in, which you could then the value would then trigger the light, or you can even trigger a fan to go on, and so they can see the immediate result of these things. When you said dive more deeply into the data production framework, we have a paper that was led by Lisa Hardy and Colin Dixon in the Journal of Learning Sciences that I'm going to refer you to, which talks about a particular student and what her relationship to that to data production. And I think that in a kind of real, I can describe it very quickly without taking up too much time here, is that when you go to make data, creating that data block was important, right? Because it used to be invisible. The system would just work on its own. But until they were intentional about thinking, I have a data bucket, I have a place where I produce them, and I can see the result of this data, and I have these data files that get collected. Unfortunately, I didn't show that in the system, but you can collect data files. You can go back and return to them and analyze them as well. So I think that when you have a kind of a perfect system that works, that it's not as fun as a system that may have different errors in it, right? And so you start the equipment itself, both the sensors and the data flow, start to push back on you. Andrew Pickering talks about the mangle of practice, right, in science practice, where machines both are measurement devices, but they also push back on you as a scientist to question your theories and your data. So I think it's that interplay between the computational system and the student that then helps students to be in that position of agency. I don't know if I answered your question, but I would like you, I'm happy to send you our paper.
I think we have time for last question.
Okay.
Okay. How could schools and parents partner to support students in computational teaching and learning, especially for very young children aged 4 to 10?
Mm-hmm. Yes, I strongly believe during the pandemic, we did not plan on doing workshops, but you can send kits out, and we really do rely on family members to get involved in that. So I feel like in order to get schools and parents to partner with students, I think part of it is providing just a very supportive environment and bringing resources, like resources and safety, kind of go hand in hand to kind of surround the child. But having conversations and asking reflective prompts would be helpful as a parent. All right, you don't want to turn into the teacher, but you want to ask some very helpful things of like, what are you doing? What are you planning to do next? How does this work? I think that would be super helpful. I also want to give a shout out to my colleagues at CodeJoy. They have a program where families and students can go to their website, and they used to have a Saturday program where they host coding sessions where families can join the program and also code together on the computer while the physical devices are in Pittsburgh. And so you don't have to build a whole robot, but you can operate a cardboard robot by joining this interface. But yes, I think parents and schools are really important, especially for younger. I have not gone younger than oh, sorry, I misread that, for really younger hands. Yes, I have done some workshops in libraries with grandmas, kind of helping out. But I think, again, it's gathering the materials and making sure everyone's safe. And there's, so that's super helpful.
Okay, thank you for a very good time control. Although I see the last question about the outlook of culturally responsive computing that you mentioned at the end of the talk. Yes. But if you can give us a little peek on that, so we can wrap up today.
Yeah. I think this is the idea that students have ideas and assets and practices to bring, and they're cultural practices that we can't expect and ever design into our systems. So if you have an approach that creates an opportunity for an open narrative for them to participate and bring their assets that they can bring on, then you would count that as responsive. Now, in terms of the responsive computing, that usually is built from culturally responsive pedagogies, which also looks at language, the languages that they use and the language choices. There are a number of resources that have been produced, and I'm forgetting the website at the moment. There's like 3 that they could be possibly on that I would be happy to follow up and send to you. If you do contact me, I'm happy to send you more information about that. But I think it's going to be a really important area to enable computational participation by everyone, to make sure people belong because they can use their own personal stories and assets.
Okay, thank you, Dr. C, for the wonderful talk. And I personally learned a lot, and I believe our audience today have learned a lot, and they can look at the videos afterwards if they have questions, and I think they can contact you anytime, right?
Very good, yes.
Yeah, okay, thank you again. Thank you again, and we'll see each other somewhere in the world or online again. Thank you.
Thank you for inviting me to speak. I really enjoyed this.
Thank you very much.